In this section, I'm going to introduce the mathematical operation known as convolution, and also I'll show how to perform convolution computations, and we'll also look at some properties of convolution. On this slide, I need to introduce a mathematical operation known as convolution. So essentially, convolution is an operation that takes two functions as operands and produces a function as its result. So looking at the definition at the top of the slide, the convolution of the functions x and h, which we denote by x star h, is defined as the function given by this particular formula here. So if we look at the left-hand side, x star h denotes the convolution of the functions x and h. So x star h corresponds to a function. Because this is a function, we can evaluate it at a point. So this is evaluating it at the point t. And what this particular formula is giving us is a way to compute the convolution result at the point t. And of course, if we compute the convolution result for every value of t, we can determine the value of the function x star h. In other words, the convolution of x with h. Now, if you want a way to think of what the convolution represents, you can think of it as a weighted average of a function. You can think of x as some function that we want to take a weighted average of, and you can think of h as somehow determining the particular weighting that we want to choose. The reason for this interpretation is if we look at what's multiplying x inside this integral, what's appearing in the integrand here, what we have here is basically a weight times our function x. So effectively, this h of t minus tau corresponds to a weighting that's being applied inside of an integral. So in some sense, you can think of a convolution as a weighted average of the function x, where the weighting is coming from this factor h of t minus tau. Now when we're performing the integration, because we're integrating with respect to tau, this means that as far as the integration is concerned, t is a constant and tau is the variable. So what we have here in this expression, h of t minus tau, because tau is our independent variable, this corresponds to a time transformed version of the function h, where h of t minus tau corresponds to taking our function h and first time reversing it, and then shifting it by t. Now in this course, the symbol star will always be used to denote convolution, not multiplication, so please do not ever use star to denote multiplication. And as we'll see, convolution plays a very important role in systems theory, and if you'll remember, the particular unit that we're covering right now is a unit on continuous time, linear time invariant systems. So as it turns out, convolution has a particular significance in the context of linear time invariant systems. And in particular, it turns out that every LTI system simply computes a convolution. The relationship between the input of the system and the output of the system somehow involves a convolution. And we'll look at this in more detail later. But for now, it suffices to say that if we're interested in linear time invariant systems, we have to be interested in convolution because LTI systems fundamentally involve convolution. At this point, I'd like to consider an example to illustrate some notational issues that relate to convolution. And in particular, I'd like to consider example x.4.1. In this example, I simply want to comment on some notational issues that relate to convolution. So for the purposes of this example, x and h denote functions, and t denotes a real number. So consider the expression x star h. What's the meaning of this expression? Well, this expression denotes a function. In particular, it denotes the function that results from convolving the function x with the function h. Now because x star h denotes a function, we can evaluate that function at a point. For example, we can take the result x star h, which is a function, and we can evaluate it at the point t. So this is what this particular notation here corresponds to. We're taking the convolution result x star h, which is a function, and then we're evaluating it at the point t. Now it turns out that the brackets that we have here around the x star h are unnecessary for grouping purposes. If we drop them, this doesn't introduce any ambiguity. And so in other words, we can rewrite the expression above using this highlighted expression here by dropping the brackets, and it makes no difference. And the reason why is if we go back to the initial expression we had, this one here, there are essentially two operations that are happening in this expression. One is we're computing a convolution due to the star, and the other is we're evaluating a function at the point t due to the t enclosed in brackets here. So there's only two possible orders in which we could carry out these operations: convolution first followed by function evaluation second, or function evaluation first followed by convolution second. But of these two orders, only one of them leads to an expression that makes sense. In other words, if we were to interpret this expression here such that we first evaluate the function h at the point t and then convolve x with that result, this doesn't make sense, because then we would be convolving a function x with a number h of t. Because h of t is a number, it's the result you get by plugging the value t into the function h. And because you can't convolve a function with a number, because this makes no sense, convolution has to involve two functions, the other way that we can interpret this expression, in other words, interpreting it with the order of function evaluation first followed by convolution, doesn't make sense. Therefore, this expression here must mean this expression here. In other words, the first set of parentheses in this expression are implied when we write this expression below. At this point, I'd like to take a brief digression away from convolution and consider the operation of addition. And in particular, what I want to do is consider the meaning of this expression and the expression below it, these two expressions. So if we look at the first expression, which involves addition, what this is involving is the addition of two functions, x and h. And if we kind of deconstruct this particular expression here, what it's doing is it's taking the function x and adding it to the function h. So x plus h, what I have highlighted here, denotes a function. Not a number, it's a function. In particular, it's the function that you get by adding the function x to the function h. Now, because x plus h is a function, we can evaluate it at a point. So what we're doing here is we're taking the result of x plus h, which is a function, and we're evaluating it at the point t. So overall, this whole expression here denotes a number. It's the number that you get when you first calculate the function, which is denoted by x plus h, and then you evaluate that function at the point t. In the expression below here, this means something subtly different. In this particular case here, what we're doing is we're taking our function x and we're evaluating it at t, which gives us a number, in particular the value of the function x at the point t. And then we're taking h and we're evaluating it at a point t, which again gives us a number, in other words, the value of the function h at the point t. And then we're adding these two numbers together. So this addition operation here is adding numbers, where this addition operation up above is adding functions. So the meaning of these two expressions is subtly different. However, both of these expressions are always equal. In other words, we always have that this particular relationship holds. And the reason for this is not magical. The reason for this is simply that this is the way that we define the addition of functions. Essentially, the left-hand side of this equation is saying this is the sum of two functions, and then the right-hand side is basically telling us how do we define the meaning of adding two functions together. And basically what this is saying is we add the functions point-wise. In other words, we add them at corresponding pairs of points. And the same sort of pattern holds for subtraction of functions, multiplication of functions, division of functions. All of these operations are defined point-wise. The reason why I want to mention this is to contrast it with convolution. Convolution cannot be defined in a point-wise manner. So in particular, what I want to consider next is an expression that looks like this. A mathematical expression like this makes no sense. The reason why is that the thing that's being convolved in this expression here, if we look, kind of deconstruct the expression, we have x of t, which is a number, because we're taking the function x, evaluating it at the point t. This gives us a number. And then the other operand of the convolution, h of t, this is a number. We're taking the function h, we're evaluating it at the point t. This gives us a number. And then we're trying to convolve two numbers. But you can't convolve numbers. Convolution fundamentally is only defined between functions. There's no way to define convolution in a point-wise manner. So an expression like this does not make sense. So avoid writing expressions like this. With all this said, though, there's a very pervasive practice in engineering to abuse mathematical notation in a number of ways. And this type of notation is often used by many textbooks in engineering. And what this expression means, in other words, if you see a textbook that writes something like this, what it means is basically, well, make your best guess. In some contexts, it may mean something like x star h. In other words, sometimes this kind of abused notation that doesn't really make any sense is intended to mean just convolve the function x with h, but don't evaluate it at a point, just take the whole function. Sometimes that notation means something like this. In other words, it's saying take the function h or x, convolve it with h, and then actually evaluate it at a point. So what you get is a number. So sometimes this expression here means a number, and yet to make matters worse, sometimes it means something entirely different. And you're probably thinking right now, well, if it can mean lots of different things, how do I know which one the person who wrote it meant? And the answer is, well, you don't know, you just guess. And essentially this is the problem with abusing notation. It often leads to situations where the meaning of a mathematical expression is ambiguous, which is clearly a very bad thing. At this point, I'd like to consider the practical matter of how to compute a convolution. So in other words, if we're given a function x and we're given a function h, how do we compute the convolution of x with h? In other words, how do we deal with this integral here, which defines the meaning of convolution? So the way we approach this, essentially what's outlined on this slide, is that you can think of it like an algorithm or a series of steps that we need to go through in order to compute a convolution. So the first thing that we're going to do is we're going to plot some graphs to help guide us in the convolution process. It turns out that this is very, very helpful to do. It makes a lot of things much clearer in terms of what we need to do in order to compute the convolution. And in particular, what we do is we begin by plotting x of tau and h of t minus tau versus tau. In other words, plot these expressions as a function of tau. The reason why we're plotting things with respect to tau and not t is when we're doing this integration, the integration variable is tau. So as far as the integration is concerned, tau is the variable, and the t that appears in this expression here is just a constant as far as the integration is concerned. So when we're integrating, tau is the variable. So this is why we're plotting things with respect to tau. And what we do to begin with is we consider an arbitrarily large negative value for t. And the effect that this will have is it will take the function h, and what we're actually plotting here is h of t minus tau, which corresponds to a time reversed and shifted version of the function h. In particular, it's time reversed and then shifted by t. So by making t a very large negative value, it's going to shift this function very far to the left on the horizontal axis. And then what we'll do is, based on the graphs we have drawn, we'll write an expression for the convolution result. And then we can integrate and find out what the convolution is equal to for this case. And then what we'll do is we'll gradually increase t. In other words, we're going to effectively take the graph of this function here and gradually shift it rightward on the axes that we have drawn. And what's going to happen is, as we gradually increase t, the form of the integrand will change. In other words, the integral that we have is going to start looking different, because as we change t, the expressions that we get in the integrand are going to vary and become different. And each time they change form, we make note of this, and this will effectively become another case to compute in the convolution. Effectively, what we do is we break the convolution into a bunch of ranges of t. And for a certain range, we get a particular result. For another range of t, we get another result, and so on. And we keep repeating steps 3 and 4. In other words, we keep increasing t, and as we do this, we'll cycle through a number of different cases. In other words, for different ranges of t, this integral will look a little bit different, and we have to compute the integration result in each case. And then at the very end, what we do is we collect together all the cases that we've identified. In other words, the convolution result for different ranges of t. We combine them all together, and as long as all the ranges of t completely cover the entire real line, then we're in business. We have the convolution result for all real t, which is what we're looking for. So in a nutshell, this is the basic steps involved. Some of this may be a little bit vague until we start to go through some specific concrete examples, but at least this gives you a little bit of a general idea how we approach the problem before we get into the specifics of doing some actual examples. At this point, I'd like to consider a couple of examples of computing convolutions, and the first example I'd like to consider is example 4.1. In this example, we're given two functions, x and h, and we're asked to compute the convolution of these two functions. In particular, the function x is given by this formula here, and the function h is given by this formula here. Now, the particular method we're going to use is the so-called graphical method, where you're going to use graphs to guide us in doing this convolution computation. So because of this, I'm going to skip to the end of the example where the actual graphs appear. Essentially, all of our work is going to be driven from these graphs. So effectively I'm going to skip over all this part here and just go to the graphs at the end. So to help guide us in this particular example, I have the formula for convolution written at the top here. And what we're going to do to begin with is we're going to use graphs to help guide us in this convolution computation. So the first thing that we're going to do is we're going to plot a graph of x of tau versus tau, and a graph of h of t minus tau versus tau. In other words, each of these two factors that appear in the integrand, x of tau and h of t minus tau, we're going to plot graphs of each of them, and we're going to use these graphs to help guide us in the convolution computation. So if we plot x of tau with respect to tau, this is relatively easy to do. We can just take the formula that we were given for x of tau and just plot it directly. If we plot it, we end up with what's shown in figure A here. If we plot the graph of the function h that we're given, just h of tau, this is the graph that's shown in figure B. Now this second graph in figure B is not directly of interest to us with respect to convolution, because if we look above here, we're not actually multiplying by h of tau. The thing that actually appears in the integrand here is h of t minus tau. So what we're really interested in is not this graph here, this graph of h of tau, but rather we want to know what the graph of h of t minus tau looks like. So what we need to do is go from this graph here, h of tau, to a graph of h of t minus tau. And there's at least two different ways you can go about doing this, but the way that I would recommend is we first apply a time reversal operation followed by a time shift by t, because the relationship between the function h of tau that's shown in figure B and the function that we really care about, which is this one shown in figure D, which is h of t minus tau, the relationship between the graph in figure B and the graph in figure D, in other words, the way that we get from the graph in figure B here to the graph in figure D here, is we first apply time reversal, and then we take the result that we obtain here, which is from time reversal, and we time shift by t to get this final graph here. So if we kind of go through this a little bit more slowly, starting from this graph here in figure B, which just comes from plotting the closed form expression that we're given for h in the original problem statement, we can then apply time reversal, which, if you remember, has the effect of flipping the graph left to right, like it basically the positive part of the axis becomes appearing on the negative part and vice versa. So this gives us this graph here that's shown in figure C, and we can figure out the formula for this exponential part of the curve here just based on the formula that we have in this graph here. And next what we need to do is to get from figure C to figure D, in other words, to go from the graph of h of minus tau, which is just the function h time reversed, to this time reversed and shifted version of h. What we need to do is take the graph in figure C and apply a time shift by t. So this is what we've done in going from this graph to this graph. We've effectively shifted this whole graph over by t. So the point that was originally at 0 in the graph in figure C, when we shift it by t, this point will move from 0 to 0 plus t, because we're adding t to everything by shifting by t. So this point here will move from 0 to 0 plus t, which gives us this point here. So the discontinuity in this function will be at t in this graph, because of the fact we've shifted by t. And we can also figure out the equation of this exponential part of the curve that appears in this graph here in one of two ways. Either we can deduce it from the formula that's given here, but the way that I recommend doing this, which tends to be a little bit less error prone, is that we can figure out the formula for this particular curve here, this exponential portion of the curve, directly from this graph here, because in going from figure B to figure D at the bottom, all we're doing is we're taking all the taus that appear in the equations on this particular figure, and we're replacing them by t minus tau. So if I just take the formula for this curve here, which is e to the minus tau, and I take all the taus and replace them by t minus tau, that gives me this thing that I've written in red here. And of course we can multiply this minus 1 into the quantity in brackets, and this gives us e to the tau minus t. So this gives us the equation of this part of the curve. And then the part of the curve over here is just a flat line at 0, so this is very easy to determine. So now we have h of t minus tau. So again, if we go up to the top here, the thing that we really care about is the x of tau plotted with respect to tau, in other words this first factor here, and then h of t minus tau with respect to tau, which is the second factor. So now we have a graph of x of tau in figure A, and we have a graph of h of t minus tau in figure D. And the graphs in figure B and C we're not going to use subsequently, because really all we care about is this graph in figure A and this graph in figure D. The graphs in figure B and C were only used as a means to finding the graph in figure D in a less error-prone way, just doing things in a few steps rather than trying to jump right to the graph in figure D. So summarizing what we've done so far, we've plotted x of tau with respect to tau, and we've plotted h of t minus tau with respect to tau. And the significance of these two graphs, these are the factors that appear in the integrand here. We have x of tau is the first factor, and h of t minus tau is the second factor. So what we're going to do in the next step or stage of convolution is we're going to use these two graphs to help guide us in computing the convolution. In other words, computing this integral here. So if you remember the process from earlier, what we need to do is we first choose t to be a very large negative value. So the consequence of this, if we choose t to be a very large negative value, that means that this graph here of h of t minus tau will be shifted very far to the left, because this point here is t. If we choose t to be a very large negative value, this will shift this graph very far to the left. So what we're going to do next is we're going to superimpose this graph here of h of t minus tau onto the same set of axes as this graph x of tau. So this is what gives us the graph that's shown in figure E. So we have t chosen to be some large negative value, so this dotted line graph, which corresponds to h of t minus tau, is shifted far off to the left relative to the graph of x of tau, which is this solid line graph here. And what we're doing with the convolution is we're taking the product of the dotted line and solid line graphs, right? Because the dotted line graph corresponds to h of t minus tau, the solid line graph corresponds to x of tau, and all this integral says is multiply them together, find the product, and then we're finding the area under that curve. In other words, we're finding the area under the product. So just by eyeballing these two graphs here that we have plotted on the same set of axes, it's fairly easy to see that when we multiply them together, the dotted line and solid line graphs, we're going to end up with a flat line at 0 everywhere. Because these two functions are never simultaneously non-zero, so when we multiply them together, we're going to get 0 everywhere. And if you integrate a function that's 0 everywhere, in other words, what we're going to have here is an integrand that's just equal to 0. If we integrate such a function, we just get 0 for the answer. In other words, the convolution result in this case will be just equal to 0. But of course we're not done yet. The subtlety here is that it's not as simple as just convolution result is simply 0. The reason why we have more work to do is that the fact that the answer is 0 here for the convolution is based on an important assumption, which is that this point here, t, is to the left of minus 1. Because if we let t be a little bit larger than minus 1, then when we multiply these two functions together, the dotted line and solid line functions, then we'll have some portion where both graphs are non-zero at the same time. Therefore, we have some non-trivial integrand, in other words, one that's not identically equal to 0, that we actually need to integrate, and we probably get some non-zero result from. So the reason that we're not done here yet is that the result of the convolution being equal to 0 is only true when t is to the left of minus 1. In other words, when the picture really looks like what we're showing in this graph. In other words, t is less than minus 1. In other words, we have this inequality here. So more specifically, in the case that t is less than minus 1, the convolution result is equal to 0. But because t might not be less than minus 1, we still need to consider other possibilities. So let's try to increase t so that it's larger than minus 1. So if you keep increasing t, that means that this point here is going to shift further and further to the right. In other words, this dotted line graph shifts further and further to the right, which eventually is going to give us something like what's shown in figure F here. So in this case, t is shifted a little bit to the right of minus 1, but it's still less than 0. So it's basically this point t is between minus 1 and 0. And in this case, we're going to get a different integral to evaluate. And we'll see this in more detail as we go through this. We'll get a different integral than what we had above, which was just simply something that's equal to 0. So if we go through this in more detail, with the picture looking in the way that it does in figure F, the only portion of the tau axis where we're going to get a non-zero result when we multiply the dotted line and solid line functions, in other words, when we compute this product here, the only place where we're going to get a non-zero result is the region that I've marked in green between minus 1 and t. Because everywhere outside of the range minus 1 to t, at least one of the functions we're multiplying is 0, and 0 times anything is 0, so we'll end up with 0. So we only need to worry about integrating from minus 1 to t. But just to be a little bit more thorough here, I'll show things with a little bit more steps just so that you can see this the first time. In particular, the integration here says we need to integrate from minus infinity to infinity. So how we're going to do this is first we'll integrate from minus infinity out here up until minus 1. So that corresponds to this first integral we're going to compute. Then we're going to integrate from minus 1 to t, which is this next integral here. And then we're going to integrate from t to positive infinity, which is this third integral here. But the observation we can make about this first integral and this last integral is that both of them are going to be 0, because this first integral here, where we're integrating from minus infinity to minus 1, in other words, we're integrating from somewhere out here at minus infinity up to minus 1, over this range, the function x of tau is always 0. So because of this, the product of these functions is 0, and we're integrating 0 here. So the answer is just going to be 0. So this whole integral would just drop out, this first one. And if we look at this last integral, it's a similar sort of thing that happens here. If we're integrating from t to infinity, so that would correspond to this point here, out to infinity, positive infinity, which is out here, over this range, the function h of t minus tau is always 0. So because of this, the product of the two functions is 0, and we're integrating 0 again. So this last integral will just drop out. It's equal to 0. And all we're really left with as actual work to do is just integrating from minus 1 to t. In other words, what's left over, which is the range that I've indicated in green here, which is the only portion where the product of these two functions will be non-zero. And in this particular case, between minus 1 and t, the equation for x of tau is given by this solid line function here. So it's just a constant equal to minus 1 over the range from minus 1 to t. So the thing we're going to substitute for x of tau in our integration that we're doing is minus 1. So you see we've substituted in minus 1 here. And then again, over the range from minus 1 to t, the h of t minus tau function, this dotted line function, is given by this exponential formula here, e to the tau minus t. So the thing that we're going to plug in for h of t minus tau in the integration here is e to the tau minus t. So that's where this comes from. And at this point, all that's left to be done is just some calculus to actually integrate this exponential. And I'm not going to go through this in detail. I'm quite confident that people here can actually integrate an exponential function, because it's one of the easiest types of functions to integrate. If you want to see the details of this, you can go back earlier in this example. It's all written out in full, the actual integration step, but it's not really very interesting to go through here. So what we end up with is basically just this result here, which we can then use some calculus to integrate. But we're not done yet, because it turns out if we keep increasing t a little bit beyond where it is here, so in other words, if you increase t beyond the value 0, so this point here, t moves a little bit to the right of the origin, it turns out that the integral we end up with is going to change form again. We're going to have a different looking integrand, therefore we have to integrate again. So the next case that we have is t is somewhere between 0 and 1. So we need to recompute the convolution in this case. So again, we do like a similar sort of process. The first thing we want to do is identify over the entire tau axis here, where is the product of these two functions, in other words, x of tau and h of t minus tau, where is the product of these two functions non-zero? Because that's all we need to worry about when we're integrating, because if you integrate 0, you just get 0. So you can see from the figure that we've drawn here, the range over which the product of these two functions will be non-zero is between minus 1 and t. Because between minus 1 and t, both the solid line and dotted line function are non-zero. So when we multiply them together, we get some non-zero function which we then need to integrate. But outside of this range, we don't need to consider what's happening, because the functions are just 0. The function we're integrating is 0. So I need to integrate from minus 1 to t. Furthermore, I need to split this interval minus 1 to t into smaller intervals, because when I go to substitute values for the function x of tau, depending on where I am in this range minus 1 to t, in some places I need to substitute in minus 1 for x of tau. In other places I need to substitute in plus 1, but I can't substitute two values, so I have to break the interval minus 1 to t into smaller pieces so that I'm only substituting one value for x of tau. So this is the basic rationale for splitting things in the way that I've done here. So I split things into two subintervals, one which is denoted by this first double green arrow here from minus 1 to 0, and then a second subinterval from 0 to t. So that corresponds to this first integral and this second integral here. So if we look at the first integral, we're integrating from minus 1 to 0, in other words, from this point here to this point here. And in this range, the function x of tau is given by a constant equal to minus 1. So this is what we plug into the convolution result for x of tau, this constant minus 1. And then also over the range minus 1 to 0, our dotted line function h of t minus tau is given, is basically this thing here, is given by this exponential function e to the tau minus t. So the thing that we substitute in for that is e to the tau minus t. And then we need to proceed on to the second subinterval here from 0 to t, in other words the second integral. So again, over the interval from 0 to t, the function x of tau, if looking at our graph here, it's just a constant equal to 1. It's this solid line function here. So the thing we plug in for x of tau is the constant 1. And also over the range 0 to t, the dotted line function, our h of t minus tau function, this thing here, is equal to t to the tau minus t. So this is what we substitute for that here. Now at this point we're still not quite done, because if we keep increasing t further, in other words keep moving t further and further to the right, what's going to happen is the integrand, in other words this thing that we're integrating here, it's going to change form again. And if it's not clear why this is so, it will become clear as we look at the next case in more detail. But as we shift t further to the right, we're going to end up with a scenario like what's shown in figure H here. In other words, we're going to end up with a different kind of situation arising in the case that t is greater or equal to 1. So if t starts to move a little bit further to the right than what we have here, we end up with a picture which looks something like this. So again, the first thing we want to identify is over what range of tau the product of the two functions, the dotted line and solid line functions, is non-zero. So you can see that the only place where the product of these functions will be non-zero is between minus 1 and plus 1, because over this range both the solid line and dotted line functions are non-zero. And we can exclude the remaining part of the tau axis, because everywhere else the function we're integrating will be 0. So this is what leads to the the integration that we have over here, where we're essentially integrating from minus 1 to 1. But we need to split this interval into two subintervals, the reason being that over part of this interval, in other words from minus 1 to 0, our x of tau function is equal to minus 1, but over the second part from 0 to 1, the x of tau function is equal to plus 1. And we can't substitute two different values for x of tau, so we have to split this interval from minus 1 to plus 1 into subintervals where we always want to substitute the same thing for each function. So I've split this into the subintervals minus 1 to 0, which is this first integral here, and then 0 to 1, which is the second integral here. And now we just need to substitute into the integrals so that we can compute the convolution. So if you consider the first integral from minus 1 to 0, over this range, our solid line function, x of tau, is just a constant equal to minus 1, so we're substituting in minus 1 for x of tau. And then the thing we substitute for h of t minus tau is e to the tau minus t, because over the range minus 1 to 0 here, our dotted line function is equal to e to the tau minus t, this exponential. So that's where this comes from here. And then lastly, we need to integrate from 0 to t over this second double arrow range here. In other words, from 0 to 1. Did I say 0 to t? Yeah, if I did, I meant 0 to 1. So we need to figure out what we plug in for x of tau and h of t minus tau. So again, we go back to our graph. Between 0 and 1, our function x of tau is this constant equal to 1. So this is why we're substituting in 1 here for x of tau. And also over this interval from 0 to 1, our dotted line function, this thing here, is this e to the tau minus t, this exponential function. So this is what we substitute for that. And again, we can compute the actual result by doing some calculus and integrating these exponentials, but this is not very interesting to do, and it's pretty safe to say probably everyone taking this course can integrate an exponential. But if you want to see the details, you can go back earlier in the example. It shows these steps as well. And at this point we're done, because this covers all the possibilities for t. If we look at all the different cases that we have here, we have t less than minus 1, and then t going from minus 1 to 0, and then from 0 to 1, and then greater than 1. This covers the whole real line. So we've computed the convolution result for all real t. So at this point we're done. The next example that I'd like to consider is exercise 4.18u. In this example, we're given two functions, x and h, and we're asked to compute the convolution of these functions. And in particular, the function x is given by this formula here, and the function h is given by this formula here. So the approach that we're going to take is the so-called graphical method. In other words, we're going to use graphs to help guide us in the convolution process. So the first thing that we need to do is we need to plot x of tau and h of t minus tau versus tau. So plotting x of tau is relatively straightforward. We can just do this directly from plotting the formula that we're given for x, which leads to the graph that's shown in figure A. To plot h of t minus tau versus tau, what we're going to do is we're going to do this in stages. It's very error prone to try to do this all in one step. So what we're going to do first is we're simply going to plot h versus tau. So we can do this very easily just by plotting directly from the formula that's given here. And this gives us the graph that's shown in figure B. Now the relationship between h of tau, which we don't really directly care about, and the function h of t minus tau, which is the thing that we really care about. The reason why we care about h of t minus tau is this is the expression that appears in the convolution integral, in other words in the integrand here. So this is the thing that's of immediate concern to us. So we need to somehow get from h of tau to h of t minus tau. And there's various ways you can do this, but the way that I would recommend, because it tends to be the least error prone, is first of all take the function h and time reverse it. So if we time reverse the function in figure B, what we'll end up with is the graph that's shown in figure C. Again, time reversal just sort of flips the graph left to right. It kind of plays the graph backwards if you want to look at it that way. So this gives us this graph here. And then what we need to do is we need to take this intermediate step here, this time reversed version of h, and then we shift it by t. And shifting by t is simply going to take each label on the horizontal axis and add t to it. So for example, this point, which is labeled 2, will become 2 plus t. In other words, it becomes this point over here. In other words, t plus 2. And then this point that's labeled in green here, we're going to be adding t to this as well. So this will change from 3 to 3 plus t. In other words, we have t plus 3 over here. So this gives us the function that we really care about, because h of t minus tau is the thing that appears in the integrand directly here. The other thing that we're going to need to know is what the equation of this linear component of the graph is. And there's various ways you can do this, but the way that I would recommend that tends to be the least error prone is because the relationship between this function here and the one in this graph is simply everywhere there's a tau here, it's been replaced by t minus tau. What we can do is we can simply observe that this linear segment here, upward sloping linear segment here, corresponds to this downward sloping linear segment here. And since the formula for this downward sloping segment is minus tau minus 2, we can get the equation of this upward sloping segment by simply taking the formula that we have here and substituting into it everywhere there's a tau, t minus tau. So basically what we've done is taken this formula here, and everywhere there's a tau, we've replaced it by t minus tau. So we get this first line, and then of course we can multiply the minus 1 into each of the terms to get tau minus t minus 2. So now we have the full graph of h of t minus tau, including both kind of the vertical scale and also the horizontal axis being labeled as well. So at this point now what we want to do is we're going to take the product of the function in figure A, x of tau, and with the function in figure D, which is h of t minus tau. In other words, we're going to basically compute this product and then integrate the result, because this is what the convolution is. It's just the area of the product of these two functions. So we're going to start out by first of all choosing t to be a very large negative value. So the consequence of this is this graph here is going to be shifted very, very far off to the left. So we're going to have something like what's shown in figure E here. And in this particular graph, if we now consider the convolution result, we're going to take the product of x of tau and h of t minus tau. So we're multiplying our blue colored function here, x of tau, times the orange colored function h of t minus tau, and then the product that we get, we're going to compute the area under that curve. But hopefully it's quite clear, if I multiply the orange function times the blue function, what I'm going to get is a flat line at 0. In other words, I'll get a function that's 0 everywhere. And if I integrate a function that's 0 everywhere, I simply get 0. So in the case of figure E here, the convolution result is simply going to be equal to 0, because the function that I'm integrating is 0 everywhere. Now, in order for the picture really to look like this, the kind of the idea that we're trying to capture with this diagram is this point t plus 3 is to the left of this point at 1. This is what makes it so that two functions are never simultaneously non-zero, and we end up with a function that's 0 everywhere to integrate. So in terms of an inequality, this means that t plus 3 is less than 1. And we can subtract 3 from both sides of the inequality, and this gives us t is less than minus 2. So in other words, in figure E, what we have is for t less than minus 2, the convolution result is 0. But we're not done yet, because t might not be less than minus 2. It could have some other value. So what we do is we continue to increase t gradually. So we're going to let t get larger and larger. So this orange function is going to shift further and further to the right. And eventually what's going to happen is the point t plus 3 is going to fall somewhere between 1 and 2. And when this happens, we get the picture that's shown here. And what we need to do is, in this particular case, we now need to compute the convolution result. So the first observation we can make in this figure F, is that the only place where the product of this orange function and this blue function is non-zero when we multiply them together is between 1 and t plus 3, because everywhere outside of this range, at least one of these two functions is 0, so therefore the product will be 0. So when we're computing the convolution result, we can essentially drop out all the range from minus infinity to infinity, except for the interval between 1 and t plus 3. In other words, all we have to worry about is just the interval 1 to t plus 3. So this is why we have these limits on these particular limits on this integral here. So what we need to do next is, in the range from 1 to t plus 3, we have to figure out what do we substitute for x of tau into the convolution formula, and what do we plug in for h of t minus tau. So we just go to our graph to get these answers and guide us. So between 1 and t plus 3, the equation for the x of tau function, this blue function here, this downward sloping linear segment here, whose formula is 2 minus tau. So the value we substitute for x of tau is 2 minus tau, and that's where this 2 minus tau here comes from. And then for the value that we substitute for h of t minus tau, we have to look at this orange function. So between 1 and t plus 3, this orange function takes on this upward sloping linear function here for its value, which is given by tau minus t minus 2. So this is what we substitute in for h of t minus tau. So over here we have tau minus t minus 2. And of course we can go through the calculus of computing this integral, actually doing the integration, but this is not really very interesting. I'm sure people can integrate this function. It's just going to give you a polynomial, which is quite straightforward. So I'm not going to go through the actual integration here. If we continue along though, because this still doesn't give us the full story, or actually maybe before we go along I should just point out that because this picture is capturing the basic essence of what's going on when t plus 3 is between 1 and 2, in other words we have this inequality here, if we subtract 3 from each of the sides of the inequality, this leads to this inequality here. So this particular result for figure F holds when t is between minus 2 and minus 1. So that's where this range here comes from for t. So now we can move on to the next case. So if I keep increasing t, what's going to happen is this orange function is going to shift further and further to the right, and eventually we're going to have a case like what's shown in figure G here, where the basic essence that's trying to be captured in this diagram is that the point t plus 2 lies somewhere between 1 and 2. In other words, this inequality here is satisfied. And now what we need to do is, in this case, we need to compute the convolution result. In other words, if the picture looks like this, what do we get for the convolution? So the first observation we make is the product of the blue function and the orange function is 0 everywhere outside of the range t plus 2 to 2. In other words, everywhere outside of the range that I've marked by this double-ended green arrow here. The reason for this is outside of this range, at least one of the two functions we're multiplying is 0, therefore the overall function is 0. So we only have to focus on integrating from t plus 2 to 2, so this is the reason why this particular integral here has the limits t plus 2 and 2. And all we need to do next is simply figure out what values do we plug into the integral for x of tau and h of t minus tau. And to do this, we simply look at the diagram that we've drawn here. So between t plus 2 and 2, the function x of tau is given by this downward sloping linear function here, which has the formula 2 minus tau. So this is what we substitute for x of tau into the integration formula. And then for h of t minus tau, we look at the orange function. So between t plus 2 and 2, this orange function is given by the equation for this upward sloping line segment here, which is tau minus t minus 2. So tau minus t minus 2 is the formula we substitute in for h of t minus tau. So that's where this tau minus t minus 2 comes from. And of course we can do the calculus of actually performing this integration, but this is not really very interesting. I think it's pretty safe to assume that anyone watching this video can integrate the polynomial that you'll get when you multiply these two functions together. And this particular case here, just to explain where this range for t comes from, We said that when we drew this diagram, the idea or essence that we were trying to capture is that this point t plus 2 lies between 1 and 2. In other words, this inequality here is satisfied. If we subtract 2 from both sides of this inequality, this essentially gives us this inequality here. T lies between minus 1 and 0. And if we continue to shift t further to the right, in other words, keep increasing t, the graph, this orange graph, will shift even further to the right until eventually we end up with something like what's shown in figure H. And in this particular case, you can see that if I multiply the blue and orange functions together, the product I get will be 0 everywhere, because the orange and blue functions are never simultaneously non-zero. So when I multiply them, at least one of them is always 0, which means the overall result will always be 0. So in this case, I'm just going to be integrating a function which is a flat line at 0. Therefore, the result of the integration is 0. So this is why we get a result of 0 for the convolution in this case. And the basic essence that this diagram is trying to capture is that this point 2 here is to the left of this point t plus 2. This is the reason why these two functions are never simultaneously non-zeros, because this point here is to the left of this point. And in terms of an inequality, we have t plus 2 is greater or equal to 2. And we can subtract 2 from both sides of this inequality, and this gives us t greater or equal to 0. So if we look at what we have here in summary, we've covered all possible values for t, because here we have t less than minus 2, and then going from minus 2 to minus 1, and then going from minus 1 to 0, and then going from 0 onwards. So this covers all possible real values for t, therefore we have all the possibilities for what the convolution is equal to, and this basically completes our solution. Because convolution is of such fundamental importance, it shows up in many different situations, and in particular it often shows up in contexts that involve linear time invariant systems. So because of this, it's helpful to know some of the properties that convolution possesses, because knowing these properties can help us more easily deal with convolution. So on this slide I have 3 properties of convolution that I'd like to introduce. The first of these properties is that convolution is commutative. Again, the word commutative relates to order of things. Does the order matter? So if I have two functions x and h, what this property, the commutative property, means is that x convolved with h is always equal to h convolved with x. In other words, if I reverse the order of the operands x and h, it makes no difference to the result that I get from convolution. The next property is that convolution is associative. What associativity means is essentially if you have multiple operations, you can group them in any order you like, you still get the same result. So in this particular case, we have 3 functions, x, h1, and h2, and we have 2 convolution operations on each side of this equation. And essentially what this is saying is it doesn't matter how you group the convolution operations, you get the same answer. So if I need to do 2 convolutions here, I can do the first convolution first, in other words convolve x with h1, and then take that result and convolve it with h2, or I could first convolve h1 and h2 and convolve x with that result. In other words, it doesn't matter how I group the operations, I still get the same result. And the last property is the property of that the convolution operation is distributive with respect to addition. So this is a similar pattern that you have with addition and multiplication. So if I have 3 functions, x, h1, and h2, and I have something like what's shown on the left-hand side of this relationship here, essentially what I have is a sum of 2 functions, and then I have a convolution that's convolving with this sum. What I can do is I can distribute this convolution operation into the individual terms of the sum to get this right-hand side here. So it follows a somewhat similar pattern as what you have with addition and multiplication, for example for real numbers. But keep in mind that convolution is a very, very different thing from multiplication. It's sort of just a coincidence that it has this similar pattern that addition and multiplication have. But nevertheless, this is a useful property to know. So at this point I'd like to consider an example, and in particular what I'd like to do is I'd like to prove the commutative property of convolution, which is essentially stated in this theorem, Theorem 4.1. In this example, I'm going to prove that convolution is commutative. In other words, I'm going to prove the result of Theorem 4.1. And what it means for convolution to be commutative is simply that for any 2 arbitrary functions x and h, it's always the case that x convolved with h is the same as h convolved with x. In other words, the order of the operands for the convolution operation don't matter. You'll end up with the same result no matter how you order the operands. So the way we go about proving this is we simply choose either the left or right hand side, and then manipulate that expression until we get it into the form of the other side. So in this particular case, I'm going to arbitrarily choose the left-hand side as my starting point. So I'm going to start with the left-hand side expression here, x convolved with h. And the very first thing I'm going to do is I'm going to expand this star notation for convolution in terms of an actual convolution integral. The star notation is very convenient for saving writing, but often it's not very helpful for doing much else. It's not very helpful for getting insight into problem solving. Almost always you need to expand out the star notation into a convolution integral. So this is the first step here. And just for our reference as we're going through this proof, I've also written out the integral that we get when we write an expression for h convolved with x. So h convolved with x is simply this integral over here in the box. So what we want to do effectively is we want to show that this right-hand side here for the expression for x convolved with h is equal to this right-hand side of this integral here for h convolved with x. So if we compare these two integrals here, you'll notice that there's some differences between them. In particular, one difference we might note is that here we have h of an expression that has two terms in it. There's t minus our dummy variable of integration. Whereas over here, h just has a single variable, which is just our dummy variable of integration. So it'd be kind of nice if we could somehow manipulate this expression here, this integral, so that it was just h of a single variable, where the variable is going to be our dummy variable of integration. So what this does is it motivates a change of variable, a very common technique in problem solving. And what we're going to do is we're just going to relabel t minus tau by a new variable name, which I'm calling v in this particular case. So I'm just defining v to be equal to t minus tau. And if I define v in this way, of course, I can rearrange and solve for tau in terms of v, which gives me this relationship here. And I can also take derivatives or differentials to get d tau is equal to minus dv. And all I do now is I just apply the change of variable. So I'm going to essentially rewrite this left-hand side, or sorry, this right-hand side here by taking all the taus and rewriting them in terms of v using the equations that are stated here. And if I do this, what I end up with is this next line here. And what I want to make particular note of is make note of the limits of integration here, which have changed from what they were originally. This is a very common mistake I see when students apply changes of variable which involve the variable of integration. The limits will always change when you do this, because if you think about it, these limits here in this integral correspond to values of v, because we're integrating with respect to v. But in the original integral that we have here, these limits here correspond to values of tau, because we're integrating with respect to tau. Now, because tau and v are different by definition, this is the whole point of doing a change of variable. It would be not very helpful change of variable if we just let v equal to tau. It wouldn't really change anything. So the whole point of this exercise is v and tau are not equal. Because of this, these limits are not going to be the same as what the original limits were here. And the particular way that we determine what these new limits should be, the ones that are highlighted in green here, is using the following logic. So to find this lower limit of integration, this corresponds to a value of v. So what we want to know is what value of v corresponds to the value of tau being equal to minus infinity. And the way we can determine this is by using this equation here. So if tau is equal to minus infinity, this means that v is equal to tau minus minus infinity, which is, or sorry, t minus minus infinity, which is equal to t plus infinity, which is what we have for the lower limit here. And then for the upper limit, it's a similar sort of strategy that we use. What we need to do is we need to figure out what value of v corresponds to the value of tau of plus infinity. So we can again use this equation to determine this. We can let tau equal to plus infinity, this upper limit, and then solve for v. So in this case, we're going to get v is equal to t minus plus infinity, which is just t minus infinity, which is the upper limit that we get here. So again, always remember whenever you're doing a change of variable, and the variable that you're changing is a variable that's used for integration, the limits of integration always change. Don't forget this. It's a very common mistake. With this in mind, we can get from this line to the next line simply by observing that in these limits here, for example, the upper limit where we have t minus infinity, the minus infinity will dominate over the t. The t is insignificant with respect to minus infinity, so we can drop the t. So we have the upper limit just being minus infinity. And similarly for the lower limit, we have t plus infinity, but the infinity term will dominate over the t. So we can drop the t, and we're just left with positive infinity for the lower limit. Now things are starting to look a bit more like the integral that we want, something that looks more like this right-hand side here, but there are a few differences. One is these limits are flipped. we want the lower limit to be minus infinity and the upper limit to be plus infinity. In other words, if you look over here, the limits are actually reversed here relative to what they are in this integral here. So that's one thing we sort of need to fix. The other thing that's different is here, there's no negative sign appearing in the integrand, whereas here, we have a negative sign, or I guess on this line here, we have a negative sign appearing in the integrand, which we'd like to get rid of. And it turns out we can fix both of these things at once by observing the following property of integration, which is that if you're integrating any function from a to b, if you swap the limits and integrate from b to a instead, the only difference is it flips the sign of the integration result. So what we can do here is we can flip these limits here, but when we do this, this is going to cause the answer to be multiplied by a factor of -1. But to compensate for this, we have to multiply by -1. But the -1 that we multiply by can be used to cancel this -1, so we get -1 times -1, which is +1, and then the minus sign drops out of the next line, and plus the limits are also the way that we want them as well. They've been swapped effectively. And at this point, we're almost to where we need to be. We can just observe that we can write these factors. We can write this factor second, so basically stick it at the end here, and then write this factor first in the integrand on the next line. So effectively, we're just swapping the order of two factors in the integrand. And once we do this, this integral here simply matches this right-hand side here. So at this point, we can just conclude this integral here is just equal to h convolved with x. And this completes the proof. There's one additional property of convolution that I'd like to introduce, but before I can do this, I need to first introduce a little bit of terminology. In particular, I need to introduce the notion of an identity operation. In math, an identity operation is simply an operation that doesn't change anything. So for example, for the real numbers, if you're adding real numbers, the additive identity is 0. In other words, if you add 0 to any real number, you get back the number you started with. So 0 is the additive identity. As another example, for real numbers, the multiplicative identity is 1. If you multiply any number, any real number, by 1, you get back the same number you started with. So this is what we call the multiplicative identity. Because convolution is so important, we might ask the question, is there a convolutional identity? Because this is probably a very useful thing to know if such a thing exists. And in fact, there is a convolutional identity, and this is essentially what's being introduced on this slide. So for any function x, we have that this particular relationship here is satisfied. And essentially what this is saying is that the delta function is the convolutional identity. Because if I take any function x and I convolve it with delta, I just get x. In other words, convolving a function with delta doesn't change anything. You just get back what you started. And you can imagine that this could be a very useful thing to know, right? So for example, if you didn't know that for real numbers that x plus 0 was equal to x, it would probably make arithmetic a lot more difficult for you to do. Similarly, if you're working with delta functions, if you didn't know that x convolved with delta was equal to x, this would make it a lot more difficult working with convolution. So this is the reason why the convolutional identity is quite important.